So, today's Wednesday. You've got the career fair today. I can see several of you are dressed up nice. That's good. Even if you're not dressed up nice, you should still go just to see what's available. I recommend taking a couple of copies of your resume, being friendly, asking people about their company, ask them what kind of jobs or internships they've got available. The last several years at the career fair, out of about 120 companies that they invite, I'd say at least 30 of them are looking to hire civil engineers. And so I can't think of a major that has a more target-rich environment over there. So please take advantage. You should definitely go over there today. That's from 12 until 4. So on Friday, you've got homework 6, which is due before class, and then we're going to have the exam in class. And I'll provide that equation sheet that I showed you last time, and you should bring your computer with Excel installed in case there's an Excel-based question. Today we're going to talk about two different things. We're going to do a demo with WaterGEMS, and then we're going to discuss the particulars of the design project. So, does anybody have any questions before we get into that? All right. So you've got Bentley WaterGEMS installed. Hopefully with the connection client running in the background, you won't have any issues starting the program. After the project is done, you may consider turning off the connection client. If you go to like startup apps, it is a way for you to tell the computer which programs begin when your computer boots up. And so if your computer's really slow at booting up, it might be that it's automatically turning on a bunch of programs that you don't necessarily need to load. That's something you could look at later, maybe, not now. But the more things you turn off from automatically loading, the faster your computer will start. So right now, the connection client, the Bentley connection client, I think probably since I just installed it, it's going to automatically be coming on. But after the project is over, then I'd disable that because I don't want it running in the system tray and using resources every time I start the computer. Okay, so we're going to begin by just looking at this example again. We've seen this example previously. This is one that we solved using the spreadsheet. Let me just pull up the spreadsheet. I hope I saved the solution. I may not have the solution handy. It's probably in the slides though. When we did this one before, we had to, of course, start with a guess flow rate through each pipe, go through that standard, here it is, go through that standard process of making sure the continuity is satisfied, setting up the whole spreadsheet, and the Hardy-Cross method with Excel is great if you don't anticipate making a lot of changes to the network. But if you do, then it can be a little bit cumbersome, and that's how WaterGEMS is so much useful to us, is it's really adept at making quick changes and seeing how the pipe network responds. So we're going to work the same example and see if we get the same flow rates that were identified using the spreadsheet method. In the end, here was the flow rates. And so this is what it looks like when you first start up WaterGEMS. And they've got a lot of these little side windows open right now that I don't think we're going to need. And I don't know why they're popping up. In previous versions of the program, they didn't automatically open up. So I'm going to close the statistics window. You can do the same. I'm going to close the terrain window. Maybe I'll leave the calculations open. Prototypes I'll close. Properties I'll close. Quick graph. Boy, it just doesn't want me to get there. Okay, now I'm getting some of that real estate back. I don't need these property grid customizations, notifications. All right, just kind of closing some of this nonsense that I don't think I'm going to need because I want this main project window to be a little bit bigger as I draw. All right, as I draw my network. So here there's this ribbon of menus and tools beneath it. And on the Home tab, we're going to start with the layout. And I've given you a handout. The paper that I've given you just is this same network. And I wanted you to have the paper copy so that it's handy as I'm working on the WaterGEMS. You have the pipe characteristics in your hand there on paper. So we're going to sketch out just a conceptual network. It's not to scale. We're just putting, like pipes in a representative way that's similar to what's on the paper here. So use this layout tool, and when you bring the cursor down into the project window, you can see that the cursor now, that is the tool for a junction. And the first thing I want to draw is a reservoir. You see here at junction A, it's showing that there's a reservoir with a water depth of 61.162 meters. So right click, and that changes the type of thing that's going to be at the cursor. And so it's at junction right now, change it to reservoir. And see now the cursor symbol changed. So I'm just going to drop it. It doesn't matter where, just anywhere. I'm going to click once and then move my cursor away a little bit, and it wants to draw a pipe. And if I clicked again, it would drop another reservoir, but that's not what I want. I want there to be a junction. So right click again, and I'm just remembering I probably should have started with something else. So press escape. There's kind of a preliminary thing that we should do every time we open up WaterGEMS, and that's make sure it's in the right units. And I just noticed down here at the bottom, it's measuring distance in feet. And this example is in SI units. So let's change that. Just to make sure that nothing gets carried over from when the units used to be in traditional, I'm going to start from scratch. So I'm going to create a new model, and see how now it's got two tabs up here. Let me just close this other one. File. I'll close all of them, actually. Close all of them. Oops, I should have said yes there. Okay, so new model and tools. So we're on the tools menu because I'm going to change the units to SI. More, options, and under here, under units, instead of US customary, I want it to be SI. Okay, that's good. And then the other preliminary thing, you may remember, I think we talked about this in fluid mechanics when we used it briefly, is we want it to use Darcy-Weisbach equation, not the Hazen-Williams. Darcy-Weisbach equation is more accurate. So if you go to Home and then Options, over here on the window where we left the options, under the base calculation options, I'll double click there, and for the friction method right now it's set to Hazen-Williams, and I want to choose instead Darcy-Weisbach. Okay, so Darcy-Weisbach SI units, and I'm actually going to close everything again. Yes. Now hopefully it'll remember, oh wait, I didn't want to save it, I just wanted to close it. So close all. Do you want to save? No. All right. It seems strange that we keep closing and reopening, but what I want to do is I want to open it when it's starting off in SI units, and now it is. So down at the bottom it's saying meters. From the very first thing I draw, I want the units to be in meters. I'm not sure if it remembered so it's still on Hazen-Williams. Change it over to Darcy-Weisbach. All right. Now we're going to start drawing. So to this layout tool, again, let's drop the reservoir. So right click to change the icon to a reservoir. Left click to drop the reservoir. Right click again to change it to junction. All right, now we're just going to draw a sketch of our pipe network. So here's A, B, C, D, F, E, connected over to C, escape, and I want to connect A to F, escape. Okay, so right now you can see by default it's labeled thing like J1, J2, J3. I can go in and rename those. I do need to put one more reservoir in. You notice on the handout I gave you that there's a reservoir down at D. So let's go to Layout, right click, Reservoir, and then right click again to Junction and connect it over here to that corner, Escape. So now all of the pipes that should exist do. They're not the right length yet, they're not the right material, they're not the right diameter, they're not labeled correctly, but they exist in the database. And we're going to go in and change all the things that it needs to know. We're going to tell it about the diameter, the length. We'll give it new labels. Does anybody have questions so far? Something you need to see again? Please let me know if you've got a question. Okay, so let's start off by changing the names. You know, instead of J1, J2, I just want to call it A, B, C, D, and so on. So here in the flex tables, the quickest way to change a lot of things at once is through the flex tables. Go to the junction flex table, and instead of it calling it J1, I'm just going to go into that table and tell it, no, that's A. And this J2 is what I want it to be, B. And J3 is C. And so on. J4, D. J5, F. J6, E. All right, so now they've got labels. That's progress. Nothing else we need to do right now with the junction table, but for the project, you're going to have to put in the actual elevation at each junction. In this example, we're assuming all of the junctions are at the same elevation. In the project, I'm giving you a map that has contours, and the elevations will be different at every junction. So this junction table is where you'd tell it the elevation. The other thing that we do in the junctions is we tell it where water is being extracted from the network. So if you look in the paper handout I've given you, water is extracted at E and at B. So we're taking water out at E and B. And so we need to tell WaterGEMS where water's coming out. So here at E, go into demand collection. So see it's got this little dot, dot, dot. Click on that, and it wants to know how many liters per second are being extracted at E. So if it's 1.6 cubic meters per second, that is 1,600 liters per second. That's how much water comes out at E. All right, we also want to tell it how much water is coming out at B. So click again on demand collection for B, and it should be 600 liters per second at B. All right, close it. So we've told everything we need to about the junctions. Let's go into the pipe. By the way, see how it's saying right now P2, P3? I'm not going to bother renaming those, but I don't want to see them. So over here, you can turn on and off labels. So right now, if you expand the pipe labels, I'm just going to tick that box and turn it off because I don't want to see those labels. They don't do anything for me. So it's disabled. Okay, now into the pipe table. All right, so you can see the start node and the stop node for each pipe. So for example, the pipe that connects A and B, we know its length is 220 meters and its diameter is 500 millimeters. So we're going to need to go in here and tell it the actual length and the diameter. So look what it thinks right now is the length. For pipe AB, it thinks the length is 62. Why do you think it has estimated that? What would it be based on? Yeah.
Just be the origin, like on the
Yeah.
sheet, and then just wherever you draw to.
Yeah, so it kept track of the coordinates of where I clicked, and it was saying, like, if you are doing a scaled drawing, then the pipe is 8 meters. But I didn't have any kind of scaled image in the background that I was drawing on top of. This is not a scaled drawing. It's conceptual. So instead of using that scaled length, I want to tell it to use a user-defined length. See, this column has user-defined length? That's what I want to turn on for all of them, is that all of these pipes have user-defined lengths. Rather than clicking them individually, I can up here at the top right-click, global edit, value, check the box. And that's a way to check the box all instantly. But now, instead of it being the scaled length that it uses, see how it's yellow now? Yellow means that it's being overridden by something else. So now I'm going to be able to put in the actual lengths. It would be simpler for me if these lengths were, I want to move where this appears. I think I can just drag it over. So you can kind of like reorder where things are displayed. Because it'd be easier for me if I've got, the things I'm changing is the diameter and the length. So I want to have maybe the length and then the diameter, because that's how it appears on my paper, like 220 meters, 500 millimeters. So feel free to sort the order that the columns appear just to make it easier for you to put the data in. Okay, so P1 connects the reservoir and A. Now we just want it to have some really short length, like 1 meter, because it doesn't actually even exist in the system. That's just a way for me to force a certain pressure at junction A. What we know about the system is junction A, the pressure is 600 kilopascals, and so that's why I put the reservoir there, is as a location for the water to be coming from and a way in the model for me to define what the known pressure is. So 1 meter in length, and let's just say that the pipe diameter is really big because I don't want there to be any head loss through that, 1,000 millimeters. All right, but pipe AB, the length 220, the diameter 500 millimeters. Okay, pipe BC, 100 and 650. Pipe CD, it's 80 meters long, 850 millimeters in diameter. DF is 200, 500. EF, 80 meters long, 700 millimeters. CE, 150 long, 600 millimeters. AF, 180 and 400. And then this last one from reservoir 2 to junction D, that pipe doesn't actually exist in the network, so I don't want there to be a lot of head loss through it. So the reason why I choose such a low length is I just want to choose something that's not going to consume pressure. So 1 meter long and 1,000 millimeters in diameter is just a way for me to make sure that whatever pressure I want there to be at D is delivered by the reservoir, and the model isn't somehow extracting pressure in that way. All right, so what we did was we defined the length and the diameter for each pipe. If we wanted to, we could rename the pipes. You know, for example, pipe 2, as it's called here, maybe it'd just be better if I called that pipe AB. And this maybe is pipe BC, pipe CD, DF, EF, CE, AF, you know. The labels aren't showing anyway, but it's maybe more natural if the label corresponds to the origin and destination, or like the two ends. In the handout I gave you, it said that each of these pipes has a equivalent sand roughness of 0.3 millimeters. So it's got Hazen-Williams C values here. Don't take that as an indication that it's going to use the Hazen-Williams equation necessarily. We previously defined Darcy-Weisbach, and it's going to use the Darcy-Weisbach equation. It just has a lot of different properties here. And by the way, these aren't all the properties that you could have for the pipe. There's more things that we could include. How do we do that? Right click. Like you could add a bunch of other types of columns. So what it's showing right now is just kind of like the default columns, but the point is that the equivalent sand roughness of 0.3 millimeters is based on the material. So let's go into these material properties and just see what is it assuming for ductile iron. So if we expand out the material properties library and scroll down to ductile iron, it says that ductile iron has a roughness height here in meters of 0.0003. Okay, that's the same as 0.3 millimeters. So yeah, we should leave it as ductile iron. Like if it was something else, like we were told it was cast iron for all the pipes, we could up here, remember, global edit and choose some other material, I guess we'd have to type cast iron. And then we could go into the material properties and see what it is for cast iron. Cast iron, oh, it's the same thing, same roughness height in its library, 0.0003. Okay, so it has the right roughness based on the knowns that we've got. All right, so it knows the size of the pipe, it knows the diameter, it knows the elevation, because this one's horizontal. We've got them labeled. We need to define the reservoirs. So let's go into the flex table for the reservoir. And reservoir 1 is this one over by junction A. It's got an elevation of the water of 61.162. Now, I selected that just because we want there to be 600 kPa at that junction. You know, that was kind of the starting point when we worked this example. The known pressure at A is 600. So in WaterGEMS, the way you force there to be a pressure at a certain location is by connecting a reservoir or a tank. So that's why I put the reservoir there. And we also need to have a reservoir at D because, you know, in WaterGEMS, you can only have water coming into the network if it's coming from somewhere. It needs like a source. And so the reservoir is an infinite source of water where the water level is not going to change by the water that you're drawing in. So in the handout I've given you, we also want there to be 57.83 meters of head at reservoir 2. Okay, so I think we've defined everything we need to tell. We've told it where the water's coming from. We've told it that water's coming out at E and at B. It knows the diameters of the pipe, the lengths, the material properties. Can anybody think of anything else that we've missed? I can't. Let's click compute. Oh, wait. Before we do, let's save our work because you never know when the program's going to crash. So save as, just save it in a location that you'll be able to come back to later. Maybe it's good to start your own subfolder as well. Don't put it on your desktop because it's going to create several files. It could get messy. So put it in a folder. I'll call this class demo. All right, and so it saved class demo. I told it to put it in C, temp, WaterGEMS. You notice it created 3 files here. A drawing file that's kind of related to how it appears, a database file that has a lot of like pipe properties and stuff, and then the project file. You need all 3 of these files to open it up again. So if you're ever like submitting something to me, then you'd need to make sure that you provide all 3 files, or like zip it up as an archive. This has a way of doing that automatically. If you do file, save to package, then what it'll do is it'll create a zip file. So let me just put in another subfolder where I save like the class demo WaterGEMS package. And so within that package, it saves, it embeds everything. So it's basically like a zip archive that has those 3 files together. So that's what you'd need to be able to share this with me. Okay, so we've defined everything. Let's compute. Click this green arrow, compute. It runs for a second. It gives you a summary. If it's green, that's good. I'm glad I didn't get an error message about not having the right license level. Did anybody get an error message having to do with license level? That's a good sign. So what are the flow rates? How do we see that? You can see it through the flex tables. If you go into the pipe tables, then it will tell you the flow through each pipe. So for example, it says AB has a flow of 580. Well, what do we know about that from the example that we worked last time? AB 0.581 cubic meters per second. That's pretty good. I'm happy with that. So like AF 419. Let's see what it says about AF. Pipe AF 419. All right, tremendous. It would be more convenient, instead of having to open up this flex table, what if we had it annotated right on our map? Let's do that. So under pipe, right click on the word pipe here, new annotation, and then it gives us some options to select from. So under field name, let's do flow absolute. Flow absolute. The reason why absolute is we don't want it to show a negative sign if it's counterclockwise. That would just be maybe a little silly, since it already has the flow directions defined with that arrow. So flow absolute. Okay, so prefix, I'm going to have Q equals, and then for suffix, it has the units. That's good. Now if I click apply, you'll notice it's going to do it right on top of the pipe, and that's a little bit hard to read. That's not the most convenient location. So maybe if I did a Y offset of 2 meters, let's see where it puts it now. Apply. Oh, that's much better. So we've got the flow rates, we got the units. It's at a nice angle, same as the pipe. All right, that's good. What else would be nice to annotate? Maybe the pressure at each junction. Okay, so now I want to do for junction, expand that, right click on the word junction, new annotation. Okay, let's select pressure. I think we just do pressure. And then for prefix, P equals, then the units. Let me do an offset of 4 meters. Let's do -2 and -2 for the pressure. And apply. Let's just see where it puts it. We may need to make adjustments. That's okay. There's no, I mean, it's never going to be perfect. It's okay. It's not like on top of other things. You can, once it does that, you can move things around. Like if you want to move the label individually, you can do that. How do the pressures compare to what we'd calculated back in this example when we did the spreadsheet? For example, it thought the pressure at F was 553 kilopascals. What does this say about the pressure at F? 552 kilopascals. Things are lining up. I think we have a valid solution. So some of the other things that you'll need to annotate when you do your project, for example, I want you to annotate the pipe diameter. So new annotation, diameter. So D equals, and then we'll do it at a Y offset of -2. Apply. Okay, that looks good. So any questions on this basic kind of really quick familiarization tour of WaterGEMS? So in our network right now, there's no junction that's less than, looks like around 500 kPa. What if we were allowed to go as low as 240? Because the design criteria says you should make the pipes smaller and smaller until your pressure is right at the limit of what's allowable. So let's say 240 kilopascals was our allowable limit. What you're going to be doing in the project is you're going to be optimizing the pipe network. That is, trying to find what's the smallest pipe diameter that will give you acceptable results. So for example, if I chose pipe AB, let me just open up only pipe AB. I double clicked on it using this little cursor here. So see this window on the right hand side? Right now the diameter is 500. Well, I could save money if I made that a 400 millimeter diameter pipe. So 400 millimeters. Okay, and now compute again. All I did was I changed the diameter and I click compute. Look what happens to the pressure at B. It goes from 564, 562. That's not much of a pressure drop, and we just saved our client thousands of dollars by reducing the pipe diameter size. What else is it, like kind of an oversized pipe? 850 millimeters. That's a pretty big pipe here at junctions at CD. So let's see if we could downsize that. Instead of 850 millimeters, what if I made that 600? How does that affect the pressures? Compute. I'll scan my network. Well, it looks like I'm still everywhere is above 240. If 240 is my minimum, I just saved a bundle by reducing from 850 to 600. So you go through this optimization process. Well, what's the next biggest pipe? EF. 700 millimeters seems pretty big. Maybe, what if I said, I'm just going to be crazy, what if a 100 millimeter pipe, what does that do to the pressures? Compute. All right. So now there's way less flow going through there. Previously, there was like 900 liters per second. So I made that pipe really small, so it just redirected the flow through other pipes. And I got away with it. The pressures are still more or less acceptable. But if I tried the same thing here for pipe CE, if I also downsized that pipe to 100 millimeters, I might be pushing my luck. If both of the pipes that are feeding junction E are really small, then now I've got a negative pressure at junction E. It says my pressure there is negative 144,000 kilopascals. That's not even physically possible. The most negative the pressure could be would be 101 kilopascals would be the most that's physically possible, because these are all gauge pressures, and so the absolute pressure limit is 0. There's no such thing as negative absolute pressure. So it's basically telling me you're going to have to make those pipes bigger. It's not saying that in so many words, but that's what I know, is that if you got a negative pressure here, these pipes need to be resized. So that's the great thing about WaterGEMS, is you're going to be able to go through this optimization process really quickly. Let's talk about the project. I'm going to be giving you a handout today, and this is probably, I think this is the 16th time I've given this project, and it's evolved over the years. I've found things that students seem to waste a lot of time on that's not educationally valuable, and I've removed those. I've tried to clarify a few commonly made mistakes, but you're not going to benefit from all that evolution if you don't read the handout. So the first thing I'm going to say is I really encourage you to read every word of the handout more than once, because there's a lot going on here, and you're not going to understand it in its entirety the first time you read the handout. But yeah, save yourself hours of frustration, and please read the handout before you start doing your design, before you start doing your analysis. We have this development that is going to be put in, and every one of you is assigned a different location. If you look at the back side, you'll notice that your name is associated with the location, the back side of the packet that I gave you. So, you know, somebody's got Sacramento, somebody's got Chicago, somebody's got Santa Fe. Did everybody get a copy of the handout, by the way? One more? All right. Would you pass that back, please? Okay, so let's talk about this map. What do you think these curvy lines are? Elevation contours. So the example we just worked, all of the elevations were the same, But in your network, the elevations are not all the same. So there's a hillside. This development is being put on a hillside. And you can see that there's, in the north zone, it's going to be a residential area and commercial area, meaning like shopping, office parks. The south zone, I think, is just strictly residential. If I remember correctly, if we look at the demand forecasting summary table, yeah, south zone is only residential area. Over here in the east zone, there's a hotel, a food processing plant, a shopping mall on the inside of the east zone. Then you'll notice that there are these things outside the city limits. There's a sports stadium, a hospital, a housing project, a golf course, a cardboard box factory. So you have to provide water at each of these green arrows. Water is going to be extracted from a pipe network at those green arrows. And by the way, these little dashed lines, that does not represent where the pipe should go. That just represents the border between the north zone and the south zone. So where should the pipes go? You figure that out. Minimize the cost. So minimize the pipe length, minimize the pipe diameter. So like you could have water going from A to B to M to C and then over to E. Just like kind of think about how do you connect the dots with the least length, because that's going to be the cheapest way to do it, is minimizing the diameter and the length. So in this design project, there's several phases. The first phase is you're going to be trying to figure out how much water will they be consuming at each of those junctions, based on things like how many people live in the north zone. So if you look at the table on the back side of the packet that I gave you, if you have Boise, so that's Boise, Idaho, I'm assigning you a population density of 150 people per hectare in the north zone. So a hectare is 100 meters by 100 meters. And the map that I've just given you is a scaled map. 1 centimeter on that map represents 100 meters. So what you should do is get a ruler and measure how many centimeters across is it and how many centimeters tall is it. So you can find the area of the north zone. You know, maybe it's 50 hectares. And if it's 50 hectares in the north zone and you're told that you've got 150 people per hectare, now suddenly you know how many people are going to be in the north zone. How much water do people use? Well, there are some kind of like basic estimates that I've provided that you can get some details about how much water people use, but I've given you kind of old data that is like a national average. But what I'm hoping is that you find better data than what I've given you. I've given it to you just as an example of what kind of information exists in the world. So here under these reference values, for example, this says that, where's a good one? Here it is. This is saying that the typical municipal water use in the United States for domestic use, 220 liters per person per day. So this was, I think, data from the 80s, and it's a national average. So how can you improve on that? You go online and you find out if there's any data about Boise, Idaho, and how much water per person they use in Boise, Idaho in like domestic kind of neighborhood type areas. Maybe you can't find anything for Boise, Idaho, but maybe you find data for Eagle, Idaho, which is a suburb of Boise. So it's like the same geographic location. People have mainly the same water use patterns. So if you find a good source for a nearby town, then that could be good. So maybe you're doing Miami. You can't find anything for Miami, but you can find Fort Lauderdale. It's largely going to be the same. So what you're going to do is you're going to try and consider all the different ways that people use water. And then you're going to develop an estimate in phase 1 of how much water is used at every location in the map. And then once you know how much water is being drawn from the network, then that'll help you to identify the optimal size. And you have to keep the pressure between 240 kilopascals as a minimum and 850 kilopascals as a maximum. So the two things that you're going to be sizing are the pipe diameters, and then also where does the reservoir go? Because if you put the reservoir really high on this hill, then that pressurizes your network. And that's a good thing to do. It's good to have pressure, but you can't go too high on the pipe network or on the hill because like at night, they're not going to be using very much water. And so you're going to be analyzing how does your pipe network behave under the condition of maximum water demand, and how does your pipe network behave under the minimum water demand. And you never want your pressures to be below 240, never want them to be above 850. And then you're also going to, in a separate phase of the project, size the reservoir. And I'll talk more about that later in the semester. So it all goes down to some of these assumptions I've given you for figuring out how much water is needed. So you're going to have to fill out this table. And so in the north zone, how many people do you have? How much water per person per day is the average daily flow rate? Well, people don't use water at just a constant average through the entire day. Like right now, you're not using any water at all. You're just sitting in this room. But you probably use more water in the evening when you're showering, washing your clothes, flushing the toilet. And on a population average, they've studied this behavior and see how the water demand varies hour by hour. And what you should use for this project is assuming that the maximum daily demand is 1.8 times the average daily demand, and then the maximum hourly demand is 3.25 times the multiplied by the average daily demand. So on this handout, you'll have the average amount of water that they're using in the north zone, liters per second. Then the peak day will be 1.8 times the average day. The peak hour will be 3.25 times the average day. And then you're also given a fire flow. I just gave that to you outright. That's one of the things I used to have students calculate is, based on the size of the house, how much water would they need to fight the fire. And I stripped that out of the project. Just figured that your time was better spent on other things. You also have to think about commercial demand. So commercial demand, what you should think of that is it's like an office park. So it's just where people go to work. And so people aren't washing their clothes there, but there are still some water demands having to do with cleaning the building, drinking water, flushing toilets. And you can find data online. Here's an example of some data about commercial uses. Okay, here's different types of commercial facilities, like an airport. Per passenger, 10 liters per passenger per day. Or for an office, per employee, 55 liters of water per day for an office building. It's got shopping center, it's got restaurant. So you just need to think about when you're putting in a new subdivision. That's effectively what this is you're like developing some raw land. Maybe right now it's just agricultural land. You're going to develop it into like a new suburb. And we just want to know at the early stages, how big should the pipes be that's going to carry the water? And you need to think into the future when this is completely built out and you know what is going on at each of these locations, how much water are they going to need? So your design condition, the maximum flow, this demand forecasting summary table is what you have to use for your for submitting the flow rates in phase one. It's going to be hand calculations that you do, and then stapled to the front of those hand calculations will be this summary table. And it's a standardized way for me to see what your assumptions are. And I have some calculations that I've done for each one of you, and I know like what's a ballpark reasonable estimate, but there is no right or wrong answer necessarily, because you may find sources of data that are different from the data sources and assumptions that I've used. So some of the things that you're going to have to take into account, for example, is that there's a golf course And I tell you the size of the golf course, and I tell you that they use 1 inch of they need 1 inch of irrigation onto the lawn of the golf course per week. And so you're going to have to think about, based on the area of the golf course and the 1 inch of depth that they need, minus the rainfall that they can expect to see on the driest month of the year, how much water are you going to have to supply to the golf course? So it's kind of like a reasoning and a logical analysis kind of a process. So regarding the golf course, I say this in the handout, but I'll reiterate it here, that you've got a certain volume of water that you have to deliver, and you're not going to be irrigating the grass when the golfers are out there on the golf course. You need to think about, like, what hours per day would they be irrigating at the golf course. And for example, a football stadium, we don't want to figure up how much water is needed in a day and then spread it out over a 24-hour period, because during a football game, the peak demand comes maybe during the halftime of the football event. So you'd have to be thinking, based on how many people are there, how many toilets might they have? How many drinking fountains might they have? How many of them are flushing at the same time? Like, how much water is used during the 25 minutes or whatever, how long a halftime is. So you're going to have to kind of go through a logical analysis at each of these locations and think, how much water do they need at a food processing plant? They're maybe not open 24/7. Maybe they're only open 40 hours per week, and I told you how much water they're consuming, but then you're going to have to figure out over what time period the water is being delivered. So let me just jump ahead to this timeline. I think you've got 2 weeks and 2 days for phase 1. This is delivered in segments so that I can give you feedback along the way. I don't want you to go too far off into left field, making mistakes, not understanding what you're doing. So the grading of the project is that half of the project is graded with the draft submissions, half of the project grade comes from the final submission. And so that gives you some incentive to think correctly along the way, but also opportunities to make corrections if necessary. So I've kept you 1 extra minute. I'll make that up to you. But please read over this, and we'll talk a little bit more. But really, I think all that you need to know is in the written handout. So please take the time to look that over. Remember that we've got an exam on Friday. So bring your computer, I'll bring the equation sheet and the test.